Welcome to Study Loop.
In this problem, we are asked to find the maximum kinetic energy in the decay of polonium from first the alpha decay process and next the beta negative decay process. For an alpha decay, let's write out the reaction. The parent atom here is polonium 218. It has an atomic mass number of 218 and an atomic number of 84. In an alpha decay, this parent nucleus is going to lose a hydrogen. Hydrogens have an atomic mass number of 4, so the atomic mass number of the daughter atom is going to go down to 214, and helium has an atomic number of 2, so our atomic number of our daughter is going down to 82. The element in the periodic table that has an atomic number of 82 is lead. So that is the daughter element plus our hydrogen atom. I'm sorry, helium atom. So in order to find the maximum kinetic energy, we're going to take the parent and atom and subtract the daughter and subtract the combined masses of the daughter and the helium atom. So writing that out, I've looked these up here in Appendix B, and we have our atomic mass of polonium 218 up here in terms of atomic mass units. So symbolically, that difference will look as follows. 218 polonium. We're going to subtract from that the mass of the daughter nucleus, which is 214 lead, as well as the helium atom or alpha particle. Right here we have a change in mass. In order to get energy, we need to multiply our change in mass in terms of atomic mass units by this conversion factor of 931.5 mega electron volts per atomic mass unit. Doing that, we find that there is an energy release of 6.114 mega electron volts. And that was the case of an alpha decay of polonium 218. On to the case of beta negative decay. Let's write out that reaction. Again, starting with our parent, polonium 218, which has an atomic number of 84. In a beta negative decay, one of the neutrons in this polonium atom is going to decay into a proton and an outgoing electron. The atomic mass number of the element, of the daughter element, will remain the same as the parent, so we can write that as 2018, but the number of protons is going to increase by 1. So the atomic number is going to go up to 85. The element in the periodic table with an atomic number of 85 is called astatine. its symbol is At. And then we also have our outgoing electron as well as an outgoing antineutrino. Looking up the atomic mass of astatine 218, we find that that mass is 218.008695 atomic mass units. So we can write out our difference equation here in order to find the energy. It's going to be a mass difference times our energy conversion factor of 931.5 mega electron volts per atomic mass unit. So symbolically, we have 2018 for polonium minus the 2018 of astatine. Now, there is an electron coming out here, so whenever I see a beta decay, I want to make sure that I'm actually accounting for all of what's going on with the electrons in this decay. So if we do a careful accounting here, we know that the mass above of the parent, which is polonium 218, that was 84. That is the mass of the nucleus plus 84 electrons. Okay, that's the case of, that's for this guy there. In addition, our daughter nucleus, or our daughter atom rather, has a mass. The mass includes of our 2018-85 astatine nucleus is the mass of the nucleus plus 84 electrons. That was those were the valence electrons surrounding the polonium nucleus. But with beta decay, we also have the an additional electron that came from the neutron that decayed into a proton. So we also have one more electron that was freed and probably filled a valence gap in the astatine atom. So we have a balanced charge now, 84 plus 85 negative charges balances the 85 positive charges in the nucleus of the astatine atom. So all our new electrons are accounted for here. So, and we have accounted for the mass of all the players in this simple two-term difference. Putting in the numbers for this, we find that the energy released in this beta negative decay of polonium 218 is 0.2590. It actually is not exactly what's in the back of the book. It's close. I checked this figure several times, and it's the best I can do. The one in the book, the answer says 0.2 259. Perhaps they include an extra 2 here. Perhaps I'm wrong, but that is the answer as best as I can report it.